Assalamualaikum and very good day everyone. This video is intended to continue our discussion on the second order system. So previously we have discussed about the various response of the second order system. So we have the underdamped, undamped response, and we have underdamped, we have as well critically damped, and overdamped. So this response is actually depending on the location of the poles on the S-plane. So let's go to some example. We have this example here. By inspection, write the form of the step response of the system in figure 4.9. So we have a system 200 over s squared plus 10s plus 200. And we have the input here. In this case, the input is a step signals. And what we need to do is we need to find the poles of the system. So what we need to do is we have to factorize the system. So we take the characteristic equation where the characteristic equation is equals to s squared plus 10s plus 200. So when we take the factor of this characteristic equation here, what we have is actually we have negative 5 plus j 13.23, and we have negative 5 minus j 13.23. What we have two components. So if we can draw on the S-plane, actually it becomes the drawings is something like this. So we have this this is the sigma, this is the j omega over here, and we have here we have poles, and we have over here, so this is negative 5, so this is actually imaginary axis. So we have 13.23, and we have here is actually negative 13.23. So this is the imaginary. We have j component over here, negative j 13.23 over here. The real part is the exponential frequency. So like I have explained previously, the exponential frequency is negative 5. Here is the exponential frequency over here. So what does it mean by the exponential frequency? When we draw, or when we do the time response, you will get this term actually when you find the output. The output in term of in the time domain, we have ct equals to k1 plus exponential negative 5t, and we have the bracket. In the bracket is k2 cos 13.23 plus k3 sin 13.23t. So the exponential frequency is actually this term, exponential frequency. Okay, and it is said that the exponential frequency also the reciprocal of the time constant of the decay of the oscillation. Basically, you remember the time constant is actually exponential negative at. When we take the time constant, we want the t equals to 1 over a. So that is why it is said that the time constant is the reciprocal of the time constant. Reciprocals mean 1 over a. This is the reciprocal of the time constant over here. By inspection from this equation, from this system where we have the step unit step input, we can expect what are the response that this system has, since it is on the it has component both on the real axis as well as in the imaginary axis. So we can say this system is actually underdamped. So underdamped meaning that the system will behave something like this. Okay, something like this. So this is damped. How do I know it is underdamped? Because the pole location is located on this region. So we go for the specification for the second order system. What you need to understand is that we have two components that you have to know, we have the natural frequency omega n, which the frequency of oscillation of the system without damping. And then we have the damping ratio, which is exponential decay frequency over the natural frequency, radian over per second. But what you need to remember is that we have this general second order transfer function, which we have gs equals to omega n square over s square plus 2 zeta omega n s plus omega n square. So this term you have to remember without fail. This term is very important here. So you need to actually memorize this. Okay. So this when you can generalize the equation for the second order system in this form. So we have b over s squared plus as plus b, and then we can find it's actually the omega n is equal to square root of b, and a is actually equals to 2 zeta omega n. We can find the poles. We can find the poles of this characteristic equation over here using quadratic formula to find the roots. So we have here negative 2 zeta omega n plus minus square root of 2 zeta omega n square minus 4 omega n square over 2. By this formula, you can find the roots, or you can find the poles, poles number 1 and poles number 2, which is in this term. Again, actually you can get this poles location, or the roots of this term, and then you can find it as these two formula over here, where the first formula here is actually for the zeta in between 0 and 1. So if we draw it on the S-plane located over here, so this is a zeta, this is S-plane, this is a omega, so this is the sigma, this is the location of the poles. So it is in between the second quadrant and the third quadrant of the S-plane. And for the second formula here is actually the poles is located over here, so it is on the real axis, where we know that when we have two poles located at different point on the real axis, the value of zeta is greater than 1. So this is how we can represent the terms here, where we have negative zeta omega n. Here we can represent it as negative sigma d, and we can represent j omega n square root of 1 minus zeta square as the j omega d. So when we plot it on the S-plane, the distance between the origin and the pole location is actually omega n, and the distance in the horizontal axis is actually negative sigma d, which is given by negative zeta omega n. So by taking cos theta, so we have theta here, and by taking cos theta, actually what we have is cos theta equal to negative sigma omega n over omega n, which we can simplify this term equals to zeta. So basically, zeta comes from this derivation. We find the cos theta, we actually find the zeta of the system. So this is the system response for the unit step input. Says that we have the Rs equals to 1 over S. So by taking the inverse Laplace of the this Ys, what we get is we get Yt equals to 1 minus all the terms over here. So this is in case of t greater and then equals to 0. Okay, we can actually find the time constant for this formula. So we know that here we have exponential negative zeta omega n t. So we know that the definition of time constant is the time it takes to for the system to decay 37% from its original values, or In other words, the time taken for the system to reach 63% of its final value. So we need to find the exponential. So when we get exponential -1, is actually equal to 0.37. So how do we get -1? So it is by taking t equals to 1 over negative zeta omega n. So when we put it into the expression, we have this term. So 1 over zeta omega n. So what we get here is something like this. So we have exponential -1. So it will result in the time constant tau equals to 1 over zeta omega n. So again, this is a very important figure that you need to really digest. So we have this. What you need to memorize is actually one quadrant, because the rest of the quadrant is actually symmetrical to each other. So what you need to memorize is actually this quadrant only. Okay, you have the second quadrant here. So you have j omega, and then at this point of location, zeta is equals to 0. You need to remember, at this point, zeta equals to 0. At this location, if the pole is unique, means it has two different poles on the real axis. So at this location, the zeta value is greater than 1. However, if the poles is located on the same position over here, what you have is actually zeta equals to 1. And in between this imaginary axis and real axis over here, so the value of zeta is actually greater than 0 and less than 1. So please remember that. And you have to remember what we call it, the response, the time response. You have to remember how the system responds. So in this location, zeta equals to 0 is actually undamped. So the plot is something like this. You have frequency that is neither decrease nor increase. And for the zeta greater than 1, what you need to remember is that you have the system that is straightly away go to the steady state without having the oscillation. As well as at this position where this is critically damped, zeta equals to 1, what you need to remember is that you have to remember that the plot is similar to the overdamped just now, but the plot is slightly, the transition response is slightly slower as compared to the overdamped. And finally, this is what we really discuss in details, the underdamped response, where the underdamped response means it had the oscillation, overshoot and oscillation at the beginning, and finally it will decrease to 0 and reach the steady state. Okay, so this is the underdamped response. So you have to remember all this. So I have explained in the previous lectures about this, where we have this location of poles with the step response. So what I discussed in the previous slides as well is actually you can refer back to this slide. So we have this slide as well as this slide. So but this slide is actually for the location of the poles that is on the right hand side of the S-plane. So this is the right hand side of the S-plane, where I said before, right hand side of the place, the system becomes unstable. So we don't want to create a system that is unstable. Okay, we can't control the system that is unstable. So in this case, the location of poles is on the right hand side. It has both the component of a real axis and imaginary axis, so it will has oscillations. But for this case, the oscillations becomes increasing over time. It does not decrease to 0, so this is not desirable in engineering design. We also have another example here. We have the poles that is located on the real axis. We have here. And what we have is actually a response that is exponentially increasing over time. So this is also the response that we don't want to. This is what we have for the underdamped system. We can see variation of response depending on the value of zeta. Remember the zeta, the closer the zeta to the j omega axis, it will have the value close to 0. And if the zeta is located near to the real axis over here, the value is close to 1. You can see here from the response, what we have is actually zeta that is close to 0, which is in this case zeta equals to 0.1. So when it's close to the j omega axis, what happens is that it will have a greater oscillation. It takes time to decay to 0. However, when we have zeta that is close to 1, in this case 0.7 for example, you can see it actually has a little oscillation only, little oscillation before it has the steady state values. This is the critically damped system where we have a zeta equals to 1, and this is the underdamped system where we have the zeta equals to 2. You can see the difference between this is the overdamped. You can see the difference between the overdamped and the critically damped, where the transient response for the critically damped is much faster as compared to the overdamped. So what you need to remember is that more oscillation will occur in response to the location of zeta that is close to the j omega axis. I think we stop here first and we continue our lesson in the next video.